Ooh, it made a noise.
We recording?
Yes.
Yes, sir.
Thank you. All right, so some of you are in physics, right?
Yeah.
Sir.
Okay, so last week somebody was talking at the end of the period about displacement. What's displacement? What is that?
It's
How far you
Yeah, it's like how far you are to the
straight line. Straight line. Just from 2 points.
All right, Dominic's sitting right here, right?
Yes, sir.
Okay. He is made up of matter, correct?
Yeah.
I am made up of matter, correct? One of the biggest science facts that you know is that two pieces of matter cannot occupy the same space at the same time, right? So if I want to occupy the space that he's occupying, what do I have to do to him? I have to move him. You just said that I have to displace him. That's what displacement is. Moving something out of the way, right? Cannot occupy the same space at the same time.
Why can't you just use yourself away? That's not the displacement, because you're displacing it right now.
What are you guys talking about?
Absolute distance from the starting point.
That's your starting point. I'm going to move you to here. So now that distance is how far I've displaced you.
You won't.
So you guys are probably going to eventually start talking about like vectors and stuff like that, okay? And vectors you deal with displacing and all that kind of stuff. But the layman's way of thinking about displacement is just moving something out of the way, okay? When you get in the bathtub, okay, what's water do when you get in the bathtub? It moves. It goes up, right? Okay, because your volume displaces the water's volume. Okay? It's got to go somewhere, okay? So that's displacement. That's what we're talking about. What I want to talk about right here with this picture, and the reason I bring this up, is because when I throw, kick, launch, drop, okay, an object, okay, the path it takes is parabolic, okay? Think about kicking a soccer ball, kicking a football, throwing a baseball, hitting a baseball. If you ever watch like a Major League Baseball game or the home run derby, all the times they'll put a graphic on top of a home run and they'll show you the parabolic arc that ball took. You guys ever seen that? Okay. With that arc that's occurring there, okay, they have what they call exit velocity. Okay, you guys seen that? Maybe a lot of you baseball people or baseball fans. And basically that means this is how fast the ball is left the bat. Okay? And going through a little bit of physics, they can figure out what is the horizontal displacement of the ball from its starting point, what is the vertical displacement of the ball from its starting point. So essentially, how far has it moved from 0, 0, the batter's box, or something like that. Does that kind of make sense? Okay? And that's what this image here shows you. All right? And I've got a lot, once you guys understand what vectors are, this will make a little bit more sense maybe in regards to what these blue things are doing, okay? But the larger those blue arrows are, okay, then the greater the velocity. So this arrow right here is representing my velocity, my initial velocity, and this is what we call a vertical component and a horizontal component of that velocity.
For pictures, we're taking sophomores N through Z. Sophomores last name N through Z. Thank you.
All right, so we're going to get rid of those vectors because it might not be for a couple weeks in physics, and really in this class, once we get into trigonometry, we start talking about those horizontal and vertical components. But it's just SOHCAHTOA stuff, okay? So when I look at that angle right there, I'm going to say I'm going to use a 57-degree launch angle. Okay, you guys ever play that game where you've got like a hill over here, and you got a hill over here, and you're a tank here, and there's a tank over here, and you've got to move your turret or whatever so that you can launch and blow up the red tank, right? Okay? And you can maybe get like 3 or 4 launches, and then it's somebody else's turn, or the red tank's turn to shoot you. Okay? The math behind that game is solely what we're talking about right now. Okay? The changing of, my angle of my turret is changing this launch angle. Okay? Maybe I fired it once, and let's fire this once, and I go way beyond that red one, right? Okay, that's not going to hit my red tank. So I'm going to reset it, and I'm going to change maybe my launch angle a little bit. Maybe I change my initial velocity a little bit, and we're going to see how good I am at this game. And I suck at this game, right? Okay, so that's not going to hit that red one either. Okay, we keep doing that back and forth until we hit that tank, right? Well, that game is being targeted using, in the background, this idea of horizontal and vertical displacement of a projectile. Okay? If I look, and I'm just going to clean things up here, I'm going to get rid of this initial velocity vector. Let's get rid of that position vector. Let's actually use that one. All right, so I'm going to change the angle a little bit, change the velocity a little bit. Okay, and that dotted line then is going to be, it's going to be the path that that projectile takes. Okay, and I'm going to pause it right there. Okay, and what happens here, guys, if I bring these, wish I could, it's frozen right now. Well, can't necessarily see what this subscript is here for this variable where my cursor is, but it's v sub y. But if you see that v sub x, what that means, okay, is that that is the velocity. It says meters per second there. But over here it says x, okay? And that essentially means that my horizontal displacement at a time of 3.32 seconds, my horizontal displacement from basically how far I've moved, the absolute distance that I've moved from 0, 0, my starting point, is 59.96 meters in the horizontal direction. Does that make sense? At that time of 3.32 seconds, my vertical displacement is currently, it looks like it says about 8.08 meters. Okay? And those two things change as time changes, right? Okay? Now, you will eventually get into, in physics, I'm not sure whether you have a lab anymore about this, but in the past, I know Mr. was it Cairns? You remember him? He would do, you guys would launch like model rockets. You make a model rocket and then you do this, you test this, okay? I don't know if you do that anymore. But if you were to do that, you guys would figure out using some formulas for finding v sub x and v sub y and that kind of stuff, depending on your launch angle, using a little trigonometry. You would find a quadratic equation that models that dotted line of that parabola. Is that okay? Okay. Now what we're going to do, what I want you to understand is what we're going to do right now is directly linked to that, but it's not the same. Okay. A lot of people want to think, because of the way this section is titled, it's titled Path of a Projectile, that what we're modeling here in a moment is the displacement horizontally and vertical, and that's not the case. What we're going to do is we're going to model a vertical displacement, but we're going to do it against time. Okay? So what happens here is we're essentially going to take all the questions we see are going to be situations where you are shooting or throwing or hitting or dropping something straight up or straight down. Okay? So what happens then is that my launch angle is 90 degrees. Okay? And I believe the reason we do it this way is because it involves a little bit of less algebra, a little bit less physics, and it allows us to actually see kind of a real life situation, a real life phenomenon that our quadratics are applicable for. Okay? So we let that be 90 degrees, and I'll show you over here on the left hand side what is happening if I were to do this. We're going to fire that object. It's going to reach a maximum height. And then think about if there's no wind, there's no friction, that kind of stuff, it's going to come straight back down where it came from, right? Okay? If we take that scenario, shoot an object straight up, okay, and let it come straight back down, or if we just dropped it from a certain height, maybe later I'll show you dropping it from a certain height. If we do that scenario, that physical horizontal vertical displacement, there was no horizontal displacement in that situation, right? Okay, if I reset that, it does not move left or right from 0, 0. It's only vertical displacement, okay? So what we're doing then, if you can see over here on this side, what's going to happen is instead of this axis being our x-axis or a horizontal displacement axis, we're going to let this be our time axis. This is still going to be our vertical displacement axis, okay? And as I fire this, okay, just kind of, I'm going to stop it right there. You see how right now it's at 20 or 19 right here? What is it over here? Same height, right? Okay, so this axis is the same as that one. But you're seeing now that this path over in the blue is not exactly the same path that we see in the yellow graph, right? And that's because on the blue one, our x-axis is a time axis. Okay? So we're seeing, let's see if I can pull this time up a little bit so we can see it. There we go. Okay. At about 1 second, our projectile has reached a height of 20. In this case, I've got it set up with meters. Okay. So right here, this point P is the ordered pair, 0.9, comma 19, or something like that. Pretty close. Does that make sense to everybody? And that's what we're plotting on the right-hand side. These over here are x's, comma y's, okay? Or horizontal, comma vertical displacement. Does that make sense? Over here, this is time, comma a y. I'm going to call it h for height, okay? But that's what we're plotting over on the right-hand side. Times against height, okay? Does that make sense, everybody? And every time I do that, no matter how and essentially no matter how I shoot this thing or launch this thing, whether it's straight up, whether I do have a different launch angle, what we're going to see on the right-hand side, that red path.
Freshmen with last names A through G, if you could please report to the auditorium lobby for your pictures. Freshmen, last names A through G. Thank you.
That red path right there, okay, is what type of shape? That's a problem, okay? So whenever we grab, when we drop, we throw, launch, kick, whatever it may be, okay, a projectile, and we graph its height against times in which this event or the situation is occurring, the path that we trace out, or the image that we trace out, will always be parabolic. And we can answer a lot of interesting questions about that scenario using that red curve, okay? But we got to figure out an equation for that red curve, all right? And what I want to do right now is just kind of let you guys see a link between that red curve and some of the things that we have written over here, okay? I look at that red curve. Let's see if we can put it back in there. And that g of x that is showing up right here is the equation for that red curve, okay? Now, if you look at this b term right here, that b term, what does that represent? Over on the left-hand side in the yellow, what is that 26 referring to? There's some information up there on the top of that screen in the yellow.
Velocity.
It's your velocity. It's your initial velocity. If I know how fast I'm basically releasing this projectile, maybe from watching a StatCast in baseball, okay? If I know what the exit velocity is, I can now have a component to my quadratic equation. It's always that b term, okay? As I change that, okay, it doesn't matter what I change this initial velocity to. I change it to 33.5, that changes to 33.5, okay? The parabola is different, okay, because the whole situation is different. But if I change it to 33.5, okay, now it's going to come back down. We're not going to see the entire maximum value of there, but it's going to come back down, and that path is parabolic, right? Does that make sense, everybody? Okay. So that component, your b term, is always your initial velocity. It's how fast you are releasing that object, okay, or what propellant you're providing. Okay. What if I launch this thing from, instead of the ground, maybe we launch it from a height of 10. My initial velocity is 17. Now my height, you see at 10, represented inside that equation, right? Okay. Now, as I've been changing those initial velocities and I change the height, there's a constant number up there that never changed. Okay. Your a term in that quadratic equation never changed, right? It was always negative 4.9. Okay. Now, we have to understand there's a little discrepancy in regards to the way I've got to show this using GeoGebra. GeoGebra does not know if I type in t It does not know that I have changed out the x-axis for a t-axis, so that's why it's still showing x's. Those should be t's up there. But what I want to show you guys is what we refer to as the position function, okay, for the path of a projectile. Okay, so this is the generic formula. It's h of t is equal to -1/2 g t squared plus v sub 0 t plus h sub 0. Okay. And there's some things in there that we're going to talk about. I want to give you that as the guide, but a lot of times when we start doing these problems, you guys are going to skip right over the -1/2 g. Okay. G, does anybody know what g represents? It's gravity. Okay. And it's the acceleration due to gravity. Okay. So acceleration due to gravity. Let's actually start over here. So the way I write this is the height at some time t. So it's gonna, that number right there is going to be the height that my object has reached at some particular time. Okay. Now working through g. Okay. Acceleration due to gravity. Does anybody know? Somebody in the last class knew that constant? You guys know that constant? Okay, so it is. I'm going to write 9.8. 9.8 meters per second, right? Or per second squared. And that's in meters. That's what we got to pay attention to sometimes in these questions. Are they giving me meters as a unit, or are they giving me feet as units? Okay. Now some of you might have been giving me maybe better approximations for that. That changes, right? Okay, it changes if I'm on top of Mount St. Helens. That's different than when I'm standing in Death Valley. Okay. The closer to the center of the Earth that I am, that obviously that gravitational pull and the acceleration due to that is a little bit different. Okay. Obviously, it's weaker the further away I am from the center of the Earth. In regards to if I'm dealing with feet, does anybody know what it is in feet? What we usually approximate it as? It's 32 feet per second. Okay? Meaning that if I drop an object within 1 second, its acceleration is 32 feet per that 1 second. Okay? When 2 seconds expire, it's now traveling 64 feet. That's the acceleration, 64 feet per second. And then the third second is 128, and it just keeps kind of doubling itself like that. Okay, that's what that per second kind of means to us. All right, so that's nice. Okay, and the -1/2 is a constant. This thing here, okay, v sub naught. Whenever you have a subscript of 0, we read that sub naught, N-O-T. Okay. Or if you want to say v sub 0, that's fine. But any subscript of 0 is the way that we mathematically represent the phrase initial. Okay? Initial whatever. So velocity is what that v represents. So sub 0 means this is initial velocity. You'll see a lot of that. Those of you that are in physics, you guys start talking about forces and all that kind of stuff. You'll see a lot of subscripts. Those subscripts are identifiers for you in regards to what types of forces, initial forces, that type of stuff. Okay, so if it's 0, we're looking at initial velocity. H sub 0, H. What did H represent over on the left-hand side of the equation? Height, right? Okay, so it's got to represent the same thing here. Okay, but what's 0 mean? Sub 0? Initial. So that's the initial height. Essentially meaning, if I'm standing on top of a building, the height of that building would be my initial height if I wanted to then kick a ball off of it, drop an egg off of it, or something like that. Okay. But -1/2 is a constant. Acceleration due to gravity is a constant. We're gonna make the assumption that the Earth is a perfect sphere. No matter where we're at on it, our gravity is going to be the same. And really, when we move around on Earth, change our elevation, it doesn't fluctuate all that drastically. Okay, so we'll be okay. But if we can use the information in our problems set up with that, we should be able to answer questions like A and B up there for this particular bullet. What I want you guys to understand is that, like I said, you're going to probably skip over the -1/2 g, and you're going to kind of memorize this: -4.9 t squared plus v sub naught plus h sub naught. That's if I'm dealing in meters. Okay. Now, if I look at that, obviously v sub naught and h sub naught, they're going to become numbers. Okay, they'll be real numbers. If I have an a term of -4.9, and I look at my v sub naught and my h sub naught, chances are they don't divide themselves out real nicely. Is that going to make sense? Okay, there's not going to be a GCF of -4.9 and too many of the v sub naughts and h sub naughts.
Freshman, last names H through M. If you could please report to the auditorium lobby for your pictures. Freshman, last names H through M. Thank you.
All right, so when that term, my A term, my B term, and my C term don't have a GCF, chances are the best way that I'm going to approach these questions is to use a quadratic formula, okay? At least when I'm dealing with meters. You could maybe multiply everything by 10 and move that decimal place, make it -49, but I think quadratic formula is probably going to be your route you go here, probably 9 times out of 10. If I'm dealing with feet, half of 32 is -16, right? Now what they're going to do is, and usually in WebAssign, they usually deal with feet because that 16 is now an integer, which is probably going to maybe work well with some chosen values of v sub naught and h sub naught. Does that make sense, everybody? Okay, so just be careful. If you're in feet, chances are it's probably going to factor. Not always going to factor. You might use quadratic formula, which still means it's going to factor, but your techniques might change varied on whether you're in meters and feet. And we will jump around, okay? We'll go back and forth. So both those are very important for us to be able to use. I'm not going to get into, because it's like your 3rd or 4th year of calculus, that you understand why that kind of general overall formula works. That's called a differential equation. But it has things to do with slopes and that kind of stuff. If you take, and you guys will learn this in calculus, if I take that h of t, either one of these that I have up here on the board, and even that one, okay, on the smart board. But if I start filling in my v sub naught and my h sub naughts, and I take what we call the derivative of that equation, okay, that gives me, so the position, that's called the position function. When I take the derivative of it, that gives me what we call my velocity function, okay? And then if I take the derivative of that, which is essentially the slope of that function, it gives me my acceleration function, okay? So position, velocity, and acceleration are all linked together with our mathematics and obviously our physics. So that's kind of maybe open your eyes a little bit to the fact that you will use this again at some point in the next year or so. So it's important that we do learn this. But it's pretty easy, once we understand that that's the general setup for our quadratic equation, it's pretty easy to take this information from there and plug it in and work this out, okay, and answer these 2 questions that are provided here in A and B. It says a bullet is fired straight up at an initial speed of 800 feet per second, okay? So I know I'm working with feet, all right? So I'm going to use that model, so h of t, the height at some time is equal to -16 t squared plus now v sub naught. Well, v sub naught's my initial velocity, right? My initial velocity here, 800 feet per second. Okay, multiply that times t. My h sub naught, do I have an initial height? No, it doesn't specify one, right? Okay, so if it doesn't specify one, we make the assumption that we're doing this from the ground, okay, or from sea level, and that would be 0, right? Does that make sense, everybody? If they tell me I'm doing it off of a 2-story building that has a height of 23 feet, then I put plus 23 on there, okay? But that's how we set up that formula that models this situation, okay? So what this does, guys, is it's saying, okay, I have some type of firearm that when I shoot it straight up, it's going to propel my bullet at 800 feet per second on that first initial firing. Okay, that bullet's going to go straight up, it's going to reach its maximum, and it's going to fall straight back down. Okay, but when we measure that against time, we measure its height, and we plot its height against time, we should get a parabolic course. Okay, so we should end up getting something that looks like that when we graph that. Okay, does that make sense to everybody? Okay, now the question here, and we'll answer question B, I think, first. I think it makes a little bit more sense to answer that question first. It says, when will the bullet reach 6,400 feet? When will the bullet reach 6,400 feet? Well, right now we have that parabola represented by this thing here. Okay? And 6,400 feet, okay, would be maybe a y value of right there, correct? And 6,400 feet is always 6,400 feet, so I'm sure y equals 6,400 feet. And now I ask myself, okay, when does the bullet reach that red line? It's 2 times, right? And you guys remember, if graphically these two things intersect, the red line and the black curve, if they intersect, that means what about their equations? This is y equals 6,400. This here is that. Okay, or I guess y, let's call it h instead. Okay? If that's the case, if these two things intersect, don't these two things have to be equal? Okay? And when they're equal, that's where they intersect, right? And we can solve for that t value of where they do intersect. So let's do that. So let's say that my height at some time is 6,400. So 6,400 is equal to now negative 16t squared plus 800t. And what do we have there? We now have a quadratic equation with an a, b, and c, right? Now it's up to you how you want to go about and solve this, but I look at that and I say, okay, 64 and 16. Now, I know it's 6,400, but I'm going to look at just the 64. 64 and 16 are off the bat, I know they divide evenly. 64 is a multiple of 16, right? Is 80 a multiple of 16? Yeah, so 800 is going to be divisible by 16 as well, correct? So I'm going to do this. I'm going to go ahead and solve for, or set this thing up equal to 0. So I'll move the 6,400 to the other side. Okay. Now understand that this top equation was this picture. When I rewrite it this way, when I move that 6,400 to the other side by hand, we're going to find those solutions to this picture. But if I were to graph this, it's a completely different picture, right? Does that make sense? Okay. But the solutions to this reside in the solutions to this. Okay, they're the same in this instance. But the reason I wanted to do that, because I see that 16 and I recognize, well, I can factor out a negative 16. And when I do that, this should be t squared. Okay, so that's going to give me 80 divided by 16 is 5. Okay, so 800 divided by 16 should give me 50. 64 divided by 16 is 4, so 6,400 divided by 16 should be 400. Okay, and this should be a negative sign. Positive divided by a negative should be negative. And I need my t there. All right, and we got 0 over here, right? Now my question to you, because some people don't know when they can do this and when they cannot do this. Can I divide both sides by negative 16 here? Yeah, absolutely. 0 is divisible by negative 16. This gives me 0. And on the right-hand side, I'm left with t squared minus 5, or 50t minus 400. Now, here's my question, though. If I had something like this, if I just had negative 16, and then we got t squared minus 50t minus 400. If I just had that, can I just let that negative 16 kind of disappear now? Can I divide both sides by that? No, because I don't have two sides there, right? Okay, so that negative 16 is not going to disappear, does not divide out to both sides, because there isn't two sides, okay? So when you're dealing with factoring, you got to know, am I factoring an expression, or am I factoring inside an equation? Because then things can start dividing out and canceling. 0 divided by negative 16. And that's what people want to say, it just cancels. It doesn't cancel, it divided out, right? Okay, it gave me 0. So they get used to doing that, and then they get over here and they want to just let that disappear. You can't. Okay? It's not an equation over there, it's just an expression. But now that thing, okay, can that factor? Oh, messed my signs up. That should be a plus sign. Plus sign. Negative divided by negative should be positive, right? So then when I look at that, so t minus 10 times t minus 40, that should multiply out to give me t squared minus 50t plus 400, right? So what's that telling me t has to be? What value of t would I get from that factor right there? 10. And from the other one? 40. So if this is my t-axis, this is my h of t-axis, okay? That point right there is 10 time, comma, height, 6,400. Is that all right with everybody? Okay. This one here would be 40, comma, 6,400. Okay. All but one time, whenever they ask me certain heights, okay, as long as my object reaches that height. So if my object, if I asked you like 12,000, when does it reach a height of 12,000? Well, if you set that up, okay, or yeah, 12,000. If I set that up and start factoring it, I'm going to find out that I get imaginary values. Okay, I get a discriminant that's negative, telling me then essentially then that those two curves do not intersect and I don't reach a height of 12,000. That makes sense? Okay, but every other time, if I asked, you know, when's it going to reach 3,200? How many solutions would it have? If 3,200 is there, how many solutions would it have? 2, right? If I asked, you know, 1,000, how many solutions would it have? 2. What if I asked 10,000? When does it reach 10,000? How many solutions do you think I might have? Maybe 10,000 is right there. We're going to have 1. So there's a situation, and that's when it reaches its maximum. There's a situation where we reach our maximum, and you have 1 solution. In every other situation, as long as they intersect, you'll have 2.
Freshman N through Z, last name's N through Z for freshman. Thank you.
All right, so what I like to do, once we've got our work done by hand, come to GeoGebra, come to Desmos, and type those things in and see if your answers make sense. So I'm looking at negative 16 x squared plus 800x. Okay, and I've already set my axes up to address the scale, okay? But that is h of t. That is our function, okay? That models that ball being shot straight up with a velocity of 800 feet per second and then coming straight back down, okay? If I type in y equals 6,400, I get that. Where do those two things intersect? Look at their intersections, that one and that one, A and B, x value of 10, height of 6,400, right? Or time value of 10, height of 6,400, time of 40, height of 6,400. Does that make sense, everybody? Okay? So that is what our initial equation would have looked like. Now, if I'm a person that says, okay, I want to type in this instead, minus 6,400, minus 6,400. Okay. So now I look at that, and remember that picture now is this new equation, right? Does that make sense? But the solutions to that should be the same as the solutions to that, right? This now I'm asking, when does this parabola cross or equal 0? What values? 10 and 40 again, right? So the solutions to this were the same as the solutions to that. So we're good. But we got to understand kind of the different graphical aspects to how, when we do 1 step or 2 steps to our algebra, how does that impact the graph? And what should I be looking at if I do go and try to model this with a graph? Okay. All right, so I'm going to go back to this one here, because I want to now answer the other part. Okay? The other part, I think it's part A, said when does the object, when does the bullet return to the ground? When does it return to the ground? Meaning that at some point it was already at the ground, right? Okay, when was it at the ground? At 0, 0, right? When we started. The initial height was the ground. So I'm going to use that thing again. Okay? The initial height was the ground. What does it mean? What number do we think about when we talk about the ground? What would the height be? What would be the vertical displacement if I'm on the ground? It'd be 0, right? So the question is, when does this thing hit the ground? Well, it would be when this thing is equal to 0, wouldn't it? Okay? Whenever you see the word return to the ground, a phrase, return to the ground, hit the ground, there, it's an English phrase that's implying the height of 0. Okay? Now, when we go through this, because we started at the ground, we launch this thing, it comes back to the ground. That should be 2 solutions, right? Every time we solve this, we should have 2 solutions. Sometimes both solutions will make sense, like this case. Sometimes they won't. We'll talk about a picture in a moment where they don't make sense. Or one of the solutions doesn't make sense. But if I do this, is this thing factorable still? Can I take out a negative 16? What else can I take out? T. Okay? And when I do that, then I'm going to have what, T minus 50, correct? Okay? Now, when I look at this, okay, couple things you can do. You can divide everything by negative 16 and get that out if you want to. But right now, what you have is you have a factor. Okay? Even though it's not a sum or a difference like the T minus 50 is, and this I think is the case that people struggle with. We look at that and say, well, it's not a T plus 50, T minus 50 thing, so I just get rid of it because it's not a factor. It's absolutely a factor. It's just not a sum or a difference. Okay? So we still have 2 terms here, 2 objects. That one times that one giving me 0. So doesn't that mean that negative 16t should equal 0? Or t minus 50 is equal to 0? Now if I solve this one, divide both sides by negative 16, gives you t to be what? T to be 0. And that's almost a trivial solution because we know that should show up because where did we launch this thing from? 0, right? From the ground. Okay? So they should start off at time 0. At time 0, I know I launched it from the ground, so that result should be 0. And if I solve this one, t is 50. Okay? Remember, t represents time, so at time 50, this thing's coming back down to the ground. And if I've got that parabola up there, remember that parabola is showing the path of that object, okay, as a height, comma, or sorry, a time, comma, some height. So the x-axis is our time axis. Okay, and the curve is showing those heights against those times, and we see through 50, then we're back to 0. Does that make sense, everybody? Okay, so everything then in the other quadrants, essentially whenever we're doing one of these problems, we're only interested in first quadrant information. Okay, because if I'm in the second quadrant or the third quadrant, what is time in the second quadrant? What kind of number? It'd be negative, right? Can we have negative time? No. Okay. What kind of distance or vertical displacement would I have in the third quadrant and the fourth quadrant? It'd be negative distance, right, in regards to heights. So we're not going to be dealing with that. We're only interested in first quadrant kind of data here, okay, when we look at these pictures. If I were to ask you, when does this thing reach a maximum? When does it reach a maximum? Okay, we have some tools in order to do this algebraically. If you guys remember, I didn't show it last lessons, but it is an Algebra 2 concept. You guys remember finding if I give you a quadratic equation, how you find the maximum of it, or the vertex of it? If we're looking at h of t is equal to negative 16t squared plus 800t. Do you guys remember that the maximum is located at the opposite of b over 2a, comma, then your function evaluated opposite of b over 2a? You guys ever seen that before last year? Formula is x equals opposite of b over 2a. That gives you my x coordinate and my vertex. Do that real quick. Opposite of B. What's opposite of B? Negative 800. Divided by negative 32. Okay? 800 divided by 32. Anybody got that? 25. Okay? 25 plugged back into this guy. 10,000. Okay? And that tells me then at 25 seconds, my projectile has reached its maximum height. And look at this graphically. That's 25 right there, right? My smart board just had to fit. All turned off. So that's 25 right there, right? I gotta do this one. I don't know what's going on. But 25 would be right there. Okay? 25 comma 10,000. How does that point right there, how does the x value of the maximum relate to the x-intercepts? It's in the middle. It's the halfway point, right? It's got to be the middle. Okay, it's the average of my x-intercepts. Is that all right with everybody? Okay, and that's something that you guys can use if you're asked questions about when does it reach its maximum. That's another way of saying what is the vertex of this parabola. Okay. We okay with that? Now let me show you what happens if I were to say I want to launch this thing from 2,000 feet. Okay? So I'm going to launch it from 2,000 feet. So my initial height then.
Pardon the interruption. This is just a reminder that during Wildcat time today, there will be an academic team meeting in Coach Grimm's room. And also, anyone interested in joining gatekeepers and helping out with the 5K, there's a meeting during Wildcat time in Mr. Gillette's room. So again, academic team in Mr. Grimm's room and gatekeepers in Mr. Gillette's room. Thank you.
All right, so I changed that quadratic formula to something like that. Plus 2,000. Okay? If I go through and I factor that, and I don't know if that's going to factor real nice. I might use the quadratic formula. But you're going to get this solution over here, right? Maybe something around 52-ish. Okay? And that's going to be a time to come back down to the ground. But what's this number here going to be? It's going to be negative. And hopefully that makes sense because right here, I'm standing on a building that's 2,000 feet, or a cliff that's 2,000 feet high, right? Okay? And for that object to reach the ground, okay, it would have to go back in time to do that. Does that make sense to everybody? Okay? So there will be situations when you factor this because of the initial height that you get solutions that are one's positive, one's negative. You gotta understand that that negative one's representing a time, and time cannot be negative, right? The way we think about it. So that's kind of an extraneous solution in that situation. However, it'd be nice if I'm asked about what the maximum is. It's still going to be the average of that x-intercept and that x-intercept, isn't it? That's what the x values are going to be for that maximum. So those are things that are going to be useful to us. Okay. The WebAssign stuff, guys, if you've logged into it, it says your grace period's expired. And so it was completely contradictory to what we were told. So what I'm going to do with that 1.4 assignment, I'm just going to kind of be done with that. Probably just go in and just award everybody 5 points for doing it, or doing what you did of it, okay? But I'm going to send you out a PDF here in a little bit with some questions on it that I want you to do for this evening's homework, okay? And they're going to represent, they're like the last 5 or 6 questions from that assignment. So I just screenshotted it off mine, and I'll send that to you. But they're practicing this. There's one about the boats. You guys see that boat one? Okay. When you're doing that one, you got to think, because it doesn't give you distances directly. You got to use distance equals rate times time. They tell you one boat's traveling like 30 miles per hour, but it's been doing it for 2 hours. So what's that distance? 30 miles per hour for 2 hours. I've traveled 60 miles, right? So maybe one leg of my right triangle is 60. They give me my other one. Maybe I work that out to be 90. And they tell me after 2 hours or whatever, they're this many miles apart. So they give me my hypotenuse, right? What is the number one theorem that you guys use with right triangles? A squared plus B squared equals C squared. So you can set that stuff up and it will develop a quadratic equation that you can factor, and that'll be your solutions.
I think you actually, I don't think it actually gives you time. It doesn't actually give you speed. You just have to use like speed as a variable, I think.
Yeah, it's like one.
Yeah, one gives you like it's traveling at x miles per hour, and the other one is 8 miles per hour more, right? So x plus 8. So then, but you still, because the hypotenuse is given to you as a distance, so you still have to take that and convert the x and the x plus 8 to distances, or change your hypotenuse to a rate. Either way is fine. We'll talk about it tomorrow. We'll do both examples tomorrow. But give it a shot and see where we're at. But they're real life applications of the quadratic formula. You can stop it if you want. I know you're jonesing to do it, right?
Yeah.
All right, we'll push it.
Should I stop it?
You can, yeah.
Shaking around a bunch.
Oh, you wasted your time. I'll
No,
stop it.
no,
Nope,
no,
nope.
no, no.